So today I'm going to be telling you about Homotopy Type Theory for Sewn Quilts, which is a work kind of building off of my master's thesis, which I completed last year at Worcester Polytechnic Institute, advised by Bohrer. So we have to give quite a little bit of background before we can get into the actual language itself. But first we're going to start off by talking about quilts. So quilts are really complicated structures, and they have a huge variety of forms that they can take. Many quilters today use computers in their design process, but there's a huge range of outcomes. So if we look at our pictures here, these are all quilts, right? From different time periods. We have one contemporary quilt by Karen Eckmeyer, where you've got like this very interesting like city design. We have an Amish quilt from 1885, which is a very geometric design that might be more similar to what you associate with what a quilt looks like. And then we also have another quilt from 1885 by Harriet Powers called the Bible quilt, which is still kind of a patch-based design, but has a very different look and structure than the Amish quilt. Our goal here with this work is to be able to represent all of these quilts equally as like kind of first-class quilts in our design tool, because currently they're not. You're kind of limited in what you can and can't represent in existing tools that use patches and kind of they rigidly stick you to a grid-based design. We're kind of getting around that by taking a topological approach, because that's going to allow us to have a lot more flexibility in terms of what we can represent, because we're not really worried about the exact geometry of what we're dealing with. So why are we interested in quilts specifically? Because mathematically it's kind of hard. You think about solving geometry problems, and that's really hard math to do. And this might actually, on the other side of things, be an actual practical application of homotopy type theory, which I believe we are still looking for askers about. I think we're still looking for a use for it. So maybe this might be one. And then culturally speaking, when we're working in STEM and computer science specifically, the choice of what we're putting our time into kind of says something about who belongs here. And I think this kind of goes for a lot of the works being presented at FARM'. It's that we're really trying to bring kind of traditionally feminine, traditionally like older, like quilting, it's all older women. That's just what it is. There's been studies about this. And we want to show that this is still a viable thing that computational people can look at and learn from. So how are we going to incorporate these homotopy type theory ideas with quilts? Our research question that we're kind of focused on is how we can represent the topological structure of a quilt in a programming language. And the way this kind of works out is that the program state is kind of the quilt in progress that you're constructing. So as you sew new pieces onto itself. The statements of the programs are the sewing operations that you're performing, and as you step through the program, you're performing those operations that kind of construct that whole quilt structure. And our core kind of analogy here is that when we have 2 points that are connected, like in our language, that means that they're on the same piece of fabric, that they've been either on the original same sheet, or they've been sewn together in some way. In future work, we expect that this language will generalize to other soft objects aside from quilts. Like even when we were working on this, there was a lot of thought about three-dimensional objects that can be constructed using a similar type of framework. And we don't explicitly disallow them, so you could use PieceWork as is and create three-dimensional things, or four-dimensional things. Maybe that's not as desirable. So a very brief introduction to homotopy is that homotopy spaces are things that, are spaces that contain points, and we can have paths between these points that we're looking at in the space. And now that we have paths in our space, we can also have paths between paths, and paths between paths, and like infinitely many paths, layers of paths. So as you kind of building upon this concept, there's a ton of mathematical structures that kind of follow from that. Omega topoi, like simplicial sets, CW complexes. We don't need to know about any of those. But there are the things that also use this kind of idea of homotopy. If we weren't using the lowest tech option, we would have a nice animation here showing how when we have 2 points x and y, we have 2 different paths, p and q, between them. And we also have this continuous deformation in the space between P and Q that we're calling R here. And all of this is just a fancy way to say that X equals Y and that P equals Q. Kind of the way that we kind of write this out in notation instead of a pretty picture is we might say that in terms of like in a homotopy type theory way of saying this, we would say that X and Y are of type A, points being an element of a type A. P and Q are of type X equals Y, so their type itself isn't a quality between P and Q. And R is also of type P equals Q. Its type is that equivalence. So the traditional type of homotopy type theory, one-level homotopy type theory, there is no distinction between 2 points that are connected and 2 points that are the same exact point. So like X equals Y and X equals X is like the same thing, even though that might not really be what you think in your head. So so that kind of stems from the univalence axiom, which is also on the slide, which basically says that when we have a function between A is isomorphic to B, that implies that A is equal to B in that type. That's actually an equivalence, and that means that A is equal to B is the same thing as A is isomorphic to B. And you're kind of fuzzing that line between isomorphic equivalence and equality, which is what we're interested in here. For our specific application, we're using two-level homotopy type theory, which keeps those two things separate. We are actually interested in being able to tell the difference between two things that are exactly the same and two things that are just connected to each other, but we still make use of the fact that we can blur those lines when we want to. So here we kind of, like throughout the rest of this talk, like we have definitional equality, which means that two things are exactly the same, versus propositional equality, which things that are connected to each other. Another useful thing in homotopy type theory is the concept of a higher inductive type. This would be another slide with a pretty animation. Unfortunately, we don't have them. But the classical example of a higher inductive type is this circle, where we have a base and a loop that connects the base to itself. And that's how you draw a circle using a higher inductive type. And you can kind of imagine how this would be extended to other shapes as well. So if you have two bases, you can create an edge. And if you have multiple edges, then you can create fabric, which is awesome. And that's what we're going to be using as the basis for our language. So why topology versus geometry? They're both about shapes, and they're both useful to talk about shapes. But the problem with geometry is that you have to get into the nitty-gritty details of where things actually are. And we're more interested in the higher level structure of the quilt itself. We focus on topology, but there are still a few little sprinkles on top of geometry just from design changes throughout the development of this language so far that will probably be eliminated as we develop this work further. So now we can get into talking about what this language actually is. It is called PieceWork, and it is homotopy type theory for quilts. And the very fundamental objects that we're dealing with in PieceWork are pieces, of course, pieces of fabric. And there are two kind of main types of fabric that we're going to talk about in PieceWork that kind of form our quilts. You can have fabric like this red rectangle here. It's one piece of fabric. It's all the same fabric all the way through. And then we also have this, this wheel here where you have multiple different pieces of multiple individual pieces of fabric sewn together, and it's still just a piece of fabric. They're kind of interchangeable, but they're also distinctly different. And that's kind of where the difference between propositional and definitional equality kind of comes in, where we're interested in saying that, yeah, now that we've sewn all these things together, yeah, they're literally the same piece of fabric now. So our basic syntax, we're not going to talk about this too much because it's really just all the things that you would like in a programming language, you know, the usual suspects. But we are going to talk about our interesting ones, which are our sewing operations: marking, cutting, and sewing. So before we can talk about how we operate on them, we can talk a little bit about what our shapes are. Shapes are defined as kind of a collection of edges. This is how you would define this nice red rectangle, who we will be seeing throughout this presentation. The requirements of being a shape are that we have to have at least 3 edges. You can't have a 2-edge shape. That doesn't make any sense. And you also have to be closed in the sense that you don't have any gaps in your edges. It's like the Jordan curve proof, where it's like, obviously it has to be a shape with a boundary. So that's cool. And what we can do with these simple shapes is that then we can form complex shapes, which are, as you can assume, are multiple different simple shapes grouped together in some way. So the way that we represent this is we have a list of shapes and then a list of the substitutions that are of edges, which are used to kind of join them together. So we might say that we're sewing the 3rd edge of S1 to the 0th edge of S2, and that gives us our complex shape, which is the join of this pink rectangle to this blue rectangle. Our sewing operations are used to basically transform our simple shapes into complex shapes, and sometimes vice versa. These are inspired by the types of actions that you would do in the process of constructing a quilt. So no operation, obviously you're not doing anything, you're just leaving your piece of fabric as is. You want to measure your fabric so that you know what your end result is going to be once you actually do something to it. You can cut fabric and you can sew fabric. And those are kind of what most things that you do in sewing boil down to, which is very convenient that it's only 3. That's a great number. So, as I mentioned before, we're going to be focusing mainly on the semantics of those 3 operations. So marking. So marking is kind of our equivalent of measuring, and it's how you might want to specify that, oh, I'm going to do this, but I'm only going to do it part way along my shape. What it does is that it divides one of the edges that make up your simple shape into 2 edges at some ratio n. And this is one of the places where those kind of more geometric things come up. It does not actually cut the fabric in any way. It just kind of produces this extra edge that you can then use to perform a more complicated cut or sew that you wouldn't have been able to do using the existing edges of the original shape. We have a little simple algorithm here, which basically, because what we do is we start with just the beginning and the end point of this edge, and then we create this one in the middle. We have a little algorithm here that basically just calculates the distance in between them and splits it and that's where you decide you're going to put your new point, but it doesn't, so it's just a simple, what's the word, just algebra to kind of calculate that, which is very nice. If we had animations, this would make a little bit more sense. But cut is now what we can do once we have that kind of midpoint split. So if you see that if we originally started with this pink rectangle and then we marked the edges, the top and the bottom edges, we could then cut in between them to create 2 new smaller rectangles based on that original shape. What it does kind of semantically is that it creates 2 new edges and divides the existing shape into 2 new shapes. One very important note is that the points that are being cut between must be propositionally equivalent. So you can't cut between a point on one shape and on a completely different separate shape, because otherwise you'd be cutting in empty air and that doesn't make any sense. So that is one strict rule that we have here. And the cut is really where this topological approach shines, because when you think about cutting through empty space and avoiding it, when you have a geometric approach, then you have to worry a lot about those kind of non-convex shapes and where you have empty space in the middle of if you have empty space in the center of a piece of fabric and stuff like that. So for example, this might not show up as well, but if you can imagine a shape that has, here you have a pentagon, and you can cut between point 1 and point 2 easily, right? That just makes sense. But imagine if instead this corner here was like down here. That wouldn't be as good, because now you have if you're cutting a straight line, you would go through empty space, which we wouldn't really want that behavior, and that's kind of one of the pitfalls of geometry. So that's why this is like really the place where we love topology. Topology is our friend. And then finally, their last main quilting operation is sewing. Sewing is probably the most simple because anytime you have two edges, you can just sew them together. We're not concerned about lengths of edges. We're not concerned about where they are, if they're on separate pieces of fabric or not. You can just always sew two edges together to form a new shape. And again, this would be very cool with our animations, but if you started with two rectangles and sewed their two edges together, like we saw in our complex shape example, you would end up with another rectangle. This is always how we create complex shapes, is by sewing two edges together. Our main cool theoretical result is that cut and sew are conveniently inverses of each other. The Homotopy Type Theory community uses quasi-inverses instead because you have to show, you have to find the specific way that they are inverses of each other. You have to find that exact specific case. And the really convenient thing is that when you kind of compose the cut operation with the sew operation, you always end up with the same shape as before, albeit with a new seam in it. And same for vice versa. If you sew two things together and then cut that exact new seam, exact edge, then you end up with the same two shapes that you started with. So that's very awesome. That's very convenient because that's exactly what you would expect to happen in real life, and it matches up with our semantics. For future work, we desire to have a type system. We've started some work on it, but it ends up with some kind of confusing and complicated syntax because you have to say whether or not something is already in. There's distinctions that we would have to develop a little bit further, like whether or not something is already in the shape versus not in the shape for some of the operations. Our work, right now it's a kind of an imperative programming language, which is not great. They're going to change that probably going forward. But luckily, there is going to be a going forward because the grant got funded based on this work, so that's awesome. I also must thank our quilting consultants. I'm a knitter, not as much a quilter, but we had some very awesome help from some quilters at WPI who were able to provide insight into the terminology and all of that. That was useful for learning more about quilts and what we should do with them. But yeah, thank you. Any questions? Ooh, lots of questions.
Thanks so much, Joshua. Lots and lots of questions. So just for a variety's sake, I'm going to start from the very back of the room and go forward.
Mm-hmm.
That was cool. Thanks.
Yeah.
Are you allowed to sew two edges of the same piece of fabric together?
Yes, you can make a cylinder or
like a Klein bottle.
Yeah.
So, what does that mean for quilting, though? I guess.
It kind of doesn't mean anything, I guess.
Okay.
So because our goal was to be as inclusive as possible, really we want to be inclusive. We kind of the opposite of approach of most programming languages. We really don't want to exclude much, if anything. We really want to enable the representation of as many different ways to sew fabric as possible, even if they might not be physically realizable. So that's kind of our approach so far. We might get more restrictive as time progresses, but not at the moment.
Hi.
Hi.
I've got two questions, but the first one's just been asked, so that's really convenient. So the second one, when you sew edges together, you say you don't care about the lengths.
Yes.
They just sew. But when you cut them, you are caring about the proportion. Why do you do that? Why not just make another point arbitrarily, sort of topologically in the middle of another edge?
So that's. I think I said at the beginning, we kind of went through some design changes as the language evolved and over the course of the year that I was working on it. And that's kind of one of those things that we were slowly kind of removing, but weren't quite able to get the finishing touches on reworking by the time that we had to submit for this conference. But it likely would not be it's not going to be part of future work where you don't actually care where the point is. Yeah.
Super cool work. I was curious, you mentioned sort of changing the flavor of language away from imperative, but boy, cutting something into two feels pretty imperative to me, right? Like the old thing is gone, you can't use it no more. So I guess, it seems like there's something about linearity here that would be super interesting. I don't know if you've thought about that in the type system. And I guess the other thing I was wondering if you could comment on more is this problem of referencing. Because once you cut, your references all might change. So how do I preserve, the accessibility of references as a program evaluates?
So to talk about the references first. We generally in the semantics and in the full paper and in my thesis, there's like very strict rules about the order of edges as they appear in a shape. And when you cut a shape, there's a very specific order maintained. So the names of those edges do change, but it's predictable. So that's how we kind of manage that. And then in terms of why we're changing away from imperative is because it was originally supposed to be logic programming, and I wanted it to be imperative because I feel like that's how quilting makes sense to me, as like how you would actually do it. But I think the future goals for this work are to kind of have it be more like generative and being able to, instead of necessarily modeling quilts that already exist, but being able to programmatically generate safe quilts.
If you want to reason about like these fine-grained notions of equality, and also want something logic programming languagey, there's been some recent work on combining equality saturation with data log that might talk to those authors.
Yeah. I have heard much about it.
Is there an inverse to the mark operation? So you put a pin in and then you can take it out?
Unmarking it? No, we don't have an inverse. I think we could add one, but there's not really a super strong reason to. If you wanted to see, if you had something marked and then you kind of wanted to unmark it, effectively all you would need to do is just there wouldn't really be a reason to unmark it unless you were trying to sew it to a whole edge that you had previously marked, but you can still do that by marking the other edge as well. Like, the way it works out is that it doesn't super matter. Yeah.
We're going to have the next speaker set up, but we're going to keep taking questions.
I'm just going to make...
Sorry. Hi, Audrey So, University of Washington.
Yeah?
I'm just curious, great talk.
Thank
and
you.
Also,
There you go.
I think it's so important to be talking about these things that are traditionally very female oriented.
Yeah.
Within this space, I really appreciate the work, and also the work that's being done in this workshop in general.
Yeah.
But I was just curious, what kinds of types would you want to add, or that you want to add to this to the language?
So the main thing is having really rigid, actual types defined for those main simple shape and complex shaped objects.
Okay.
The whole thing, everything is a shape. There's no way to get out of that. So all of it's simple in concept, hard in practice. But yeah, we were mostly focused on the semantics, just because what does it even mean to cut a piece of fabric?
Yeah.
Yeah.
Ron Minsky, Jane Street.
Hi.
Hi. So fun talk. I'm curious if you have ideas for the future of the project, how one of the nice things about having a kind of computational representation of something is that you can then do something with it, right? And I'm kind of wondering, it seems like if the goal is to have a language that's designed that lets you describe things that are maybe not physically realizable. So one thing that maybe I guess you don't do from there is go from the high level design to compile down to a thing you could feed to a quilting machine.
Yeah.
So I'm wondering what do you want? What are the ideas of how to kind of take advantage of having this kind of computational representation? What do you do with the?
So one thing that we were thinking of is that there's a few other people at WPI who do more quilting related work, and some of them have created tools for digital design, and which is very popular among quilters. Quilting itself is a very manual task. There is no obviously you're using a sewing machine, but you're not automating sewing the pieces together. That's not really something that happens. So what we're kind of thinking, the kind of application that we were thinking of is using this type of model as the back end for a quilt design tool. Digital drawing, basically.
We're a little over time, but I'm just going to keep taking questions because we were late for tech.
Yeah.
So it's terribly sorry to Stephen.
Hi, Katie Casamento from Portland State University. I had kind of one observation and one question, both about the equality, which is, and
Sure.
also, as everyone else said, really cool talk. The one observation is you talk about the conversion from a propositional equivalence to a definitional equality. That sounds like the J eliminator. If the standard sort of like eliminator for a propositional equality type gives you sort of a scoped conversion from propositional equality to definitional equality. So that was just kind of an observation that seems related to kind of like in a traditional dependently typed language pattern matching on your propositional equality to reduce it to REFL, and then in that context you've got a definitional equality.
Yeah, in like the full paper, we did talk. I talk a little bit more about how you kind of go from like a complex shape that has a ton of different subshapes in it to being like, actually, I don't care about the subshapes at all. What is just the outline?
Cool,
So,
yeah. And then the other question, which is pretty vague, but is I've got several different kind of intuitions for propositional equality, and a brand new one here is as kind of a separator between two other spaces. That you've got this propositional equality that is like a boundary between things. And I'm just curious if you have anything to say on that intuition sort of in other settings as well. The idea of an equality as a boundary or a separator or something.
So I think something really subtle is that most of the time within a complex shape, there's actually two edges there. So it's more of like you have, I guess, a hole in a space. That's another space inside of it, and then it's it happens to be right next to another hole of whatever. And we're saying that these edges kind of line up to each other, but there is probably actually some kind of, I guess, material in between them. So I think that's. I don't really know if it really. I don't really think I have a ton of insight for you about how that actually like works in other contexts, but the way that I think about it is mostly that you have kind of a seam, like an actual physical seam. Like if you look at your clothes, you have like a kind of a lump or a bump where you've sewn two pieces of fabric together. And that kind of how you set, even though it's definitively made out of the pieces of fabric that were sewn together, and it's not anything different, but it's also not the same. So
yeah, very interesting. I'm gonna have to ruminate on equalities as seams.
Yeah.
Thank you.
Yeah, no problem.